Good morning. So we are going to finish up chapter 9. Just a second. So we did the Lewis dot structures last time, and now we're moving into the VESPR theory, which is going to help us to visualize these compounds and molecules in 3 dimensions. So a couple things. Hold on one second. Just opening up the syllabus. I don't want to tell you something that isn't true. Share my screen with you all. Okay, so yes. So you do have your 3rd test on starting on Sunday through Monday. So make sure you're working on taking that. You do have the VESPR, this lab due on Sunday as well. We'll go over some of the VESPR stuff today in there. Do you know that Thursday is the first day for early voting? So you can go Thursday, or maybe you want to go Friday. Sometimes the very first day is a little sticky. The thing that's really nice about North Carolina is that, yes, voter registration ended because you have to register to vote in this country. You don't just get to vote. You have to go through another hoop before you can vote. So you have to register. That ended on October 9th, but in North Carolina, we do have registration the same day you early vote. So if you go to your polling site and you're not registered to vote, because I'm sure there's a couple of people out here who are like, oh, I want to vote, but I didn't register, I want, whatever. Well, you don't have that excuse. You can actually go to one of these voting sites. So I'll show you this here. This is for Buncombe County, but it has it for all the other surrounding areas. And I'm going to put the link in the chat. And so you click on here, and there's this thing over on the left that says early voting locations, one-stop site lookups. So a one-stop site lookup means that you can go there, you can register to vote if you're not registered, and you can vote on the same day. So you do need to have proof of address. So not a piece of junk mail, but like an actual piece of like a bill or something, legitimate piece of mail. But let's say you live in Henderson County like I do. All right, we'll find our site. And I live in like the Fletcher area, so Etowah Library is probably where I'm gonna go vote on Thursday. If you're a little bit farther south, you may find that one of these works better, or actually no, Fletcher Town Hall is where I'm gonna go. I'm not going to Etowah. So useful, really useful site. I recommend getting on there and voting. All right, let's get back to some chemistry. So we talked all about Lewis dot structures. Now we're going to move into the second half, which is predicting the shape of these molecules. The theory is called, you'll hear me call it VESPR theory. VESPR just stands for valence shell electron pair repulsion theory. Okay. So VESPR theory tells us that electron groups, and what we classify as an electron group, is a lone pair, a single bond, or multiple bonds. Okay, so a double bond is considered one electron group. A triple bond is considered one electron group. It's an area of electrons that can't break up from each other. And we would call that a group. So what the VESPR theory tells us is that these electron groups, because they all hold electrons which have negative charges, they want to get as far away from each other as they possibly can. And so this repulsion of the negative charges around the central atom helps to determine a predictable geometry for the molecule. So if there's 2 electron groups, you're going to see a very specific type of shape. If there's 4 electron groups, you're going to see a different type of shape. So let's look at this situation here, CO2. So before we get into CO2, I want you to do the Lewis dot structure for CO2. So I'm going to give you 3 minutes just to get the Lewis dot structure for CO2 done, just to re-practice all that Lewis dot structure stuff. CO2. Okay, so for CO2, we're going to draw the Lewis dot structure. We first can calculate the number of valence electrons. So carbon has 4, oxygen has 6, and there's 2 of them. So we should have 16 electrons to play around with. Carbon I'm going to put in the center. Oxygens I'm going to put on the side because it creates a balanced shape. I'm going to stick them together. Then I'm going to make the outer guys happy first and then work towards the inner guy. So this oxygen has access to 2. So let's give him 6 more so that he can have access to 8. This oxygen over here, let's give him access to 8 as well. Now we're at 2, 4, 6, 8, 10, 12, 14, 16. 16 electrons are on the board, so I can't add any more electrons. Oxygens are happy. Carbon right now is not happy. He only has access to 4 electrons, but I can't add 2 more electrons. So what ends up having to happen is that these oxygens will need to share one of their pairs and move it over here. and over here. Double count whenever you're making triple bonds, double bonds, that you still have the same number of electrons, 2, 4, 6, 8, 10, 12, 14, 16, still have 16 electrons. Oxygen is happy. Oxygen is still happy, and carbon is now happy with 2, 4, 6, 8. Okay, so everybody's good here. So how that relates to VESPR theory. Oh no, you guys don't want to do that. So when looking at CO2, I would say that this shape has 2 electron groups. Now, remember, an electron group is an area where there's electrons that can't be broken up from each other around the central atom. So looking here, this is an electron group, and this is an electron group. Sometimes they're called electron domains, same thing. So whenever you have 2 electron groups, how can those 2 things get as far away from each other as they absolutely possibly can? Well, it would be like the situation of a tug of war, right? If you've got one end of the rope and I've got the other end of the rope, there isn't any way for us to get farther away from each other in that scenario. So it would be 180 degrees, so you do need to know the angle, and we would call this geometry linear geometry. So that one's not too bad to visualize. 2 electron groups give us a linear situation. Let's move on to the next type of geometry. I'm not going to have you guys do the Lewis dot structure for every single one because kind of waste some time. So we're just going to move through some of these. So the next one here, H2CO. I probably wouldn't give you guys this structure to do as a Lewis dot structure. So don't get alarmed if you're looking at that going, ooh, I don't know how I would do that. Probably wouldn't give it to you, but this is what the structure looks like, okay? So when counting up my electron groups, only look at what's happening on the central atom. So do you see how there's these lone pairs on this tail oxygen? Those don't affect the shape. So ignore those. We only want to see what's happening off the central atom. So there's 1 domain, there's 2 domain, and there's the 3rd domain. Remember, double bond, keep it together. Triple bond, keep it together. So this thing has 3 domains. There aren't any lone pairs on the central atom. So anytime we have 3 electron groups, the distance is roughly 120 degrees. We would call this geometry trigonal planar geometry. Trigonal because there's 3, like a triangle. Planar because they're all happening on one plane. So it's like a flat pizza that is cut into 3 very large slices. Now, this double bond does have more electrons than the single bond, so it has a little bit of a stronger negative charge. So it does push on these bonds slightly more. But for the sake of this, we're just going to say it's all equal. Okay, they're all 120. So 2 electron groups, linear. 3 electron groups, trigonal, planar. Let's move on to 4 electron groups. Okay, if a molecule has 4 electron groups around the central atom, like this thing here, CH4, which is methane, we are going to call this thing tetrahedral. Now, this is really important. When it's in 3 dimensions, this is how it would look if we were to draw the Lewis dot structure on a flat piece of paper, right? But this is not what's actually happening in real space, because this would be, I would call this like square planar or something, which does exist as a shape, but not for this class. But I would call this square planar. Those 4 groups. So there's 1, 2, 3, and 4. Those are not as far away from each other as they possibly can be, because we can move in 3-dimensional space. So things can come forward and back when we're in 3-dimensional space. We're sort of locked in when we're on this piece of paper here, but in real life, this is what the shape looks like. So it is, because the angle here is 90 degrees. But if we move it into a tetrahedral shape, we can actually get 109.5 between those four groups. Think of this shape as like a little pyramid, okay? It's got 3 points on the bottom, and then it's got one boop sitting on the top. So 4 electron groups around the central atom, we're gonna say it has a tetrahedral geometry. Now, one thing that we haven't seen thus far is a situation where there's a lone pair of electrons on the central atom, like water, looks something like this, and it has 2 lone pairs on the central atom. So now we're going to talk about what happens if there's lone pairs. It gets a little bit more complicated. If there are no lone pairs, real easy. It's going to be linear, trigonal, planar, or tetrahedral. Okay, let's say that there is a lone pair of electrons. So we've got this thing here. Now we need to talk about 2 different things. We've got this thing called molecular geometry and electron geometry. The electron geometry is talking about how many electron groups there are. Okay, so this is referring just to electrons. We're only looking at electrons for electron geometry, hence the word electron, electron. What is happening with the molecular geometry is that we're going to see how the atoms themselves are arranged. So this is going to be a little bit different than what we have done thus far. So when looking at this molecule here, okay, we've got ammonia. When I'm looking at its electron group, or rather its electron geometry, I got to figure out how many electron groups there are. So I've got 1, 2, 3, and I do include the lone pairs, so I have 4 electron groups. So how are the electrons structuring themselves? Well, the electrons are in a group of 4. That gives us tetrahedral. Okay, they're making this pyramid shape, tetrahedral. But the molecular geometry is going to get a little bit funky. What are the atoms themselves doing? Well, I've got an atom here, an atom here, and an atom here. But I don't have an atom sitting on the top with those lone pairs. The lone pairs are still important because they're pushing these guys down, but there's no atom in that shape. So this is what the atom, or rather the molecule itself looks like. And we call this thing trigonal pyramidal. Trigonal pyramidal. Why is it a trigonal pyramidal? It's not trigonal planar. Do you see how these little 3 guys are pushed down? It's no longer the flat pizza, okay? It's been pushed down into this little pyramid shape. So anytime you've got a situation where you've got 4 electron groups, but one of them is not bonded, we get a trigonal pyramidal shape. Any questions on this shape? I know this gets a little bit funkier when we add the lone pairs. Just remind yourself, if there's a lone pair, your electron and your molecular geometry are going to be different. Speaking of that, I want to hop back real quick to the previous slide. So looking at this, are there any lone pairs on the central atom? No. So how many electron groups are there? There's 2. So we would say that the electron geometry is linear. How many atoms are there? 1, 2 attached to both of those. So I would say that the molecular geometry is also linear. So just know that if there aren't any lone pairs, this and this, the electron and the molecular, will be the same. It differs when we get to anything with a lone pair. Same thing with this. I have 3 electron groups and they're all bonded to an atom. So my electron geometry is trigonal planar. My molecular is also trigonal planar. Same thing here, right? 4 groups and 4 atoms attached to every group, tetrahedral, tetrahedral. This is where it differs when we get a lone pair. Let's look at another situation with a lone pair. So water. Water has 4 electron groups, just like the previous one did. Let's count them out. 1 here, 2 here, 3 and 4. Lone pairs you count separately. So don't count 4 electrons as one lone pair. So the electron geometry for water would be tetrahedral. Why? Because I still have 1, 2, 3, 4 groups of negativity that are making that tetrahedral shape. But then what we want to do when we are talking about the molecular geometry is we want to kind of ignore these and look at the remaining shape. What is the remaining shape? It forms a bent structure like this. Now I know on this page here, when we've written it on paper, it looks like it's flat, right? It looks like it's linear, but it is not linear. You have to think about this in 3 dimensions. So these 2 groups here are pushing down on those hydrogens to give it a kinked shape or a bent shape. Any questions on that? On this idea of a bent shape? Sometimes instead of bent, they call it a V shape. V shape. Why? Because it makes a V. Okay, so bent or V shape can be used interchangeably. So normally I would have you guys memorize all the shapes, but you know, so is 2020, so you get a little bit of help here. So this table, which is in your text, has all of that stuff summed up together. You may want to have access to this as far as being able to name these things. All right, 10-1. So let's do a couple of these. All right, I want you to do SO2. So I want you to do the Lewis structure. I want you to tell me its electron geometry. And I want you to tell me its molecular geometry. And then I also want you to do, start working on that one and I'll come up with another one. So we got SO2 and I also want you to do pH 3. pH 3. Okay, so for SO2, as far as the number of electrons we have to mess around with, 18. Can't get that number right, it throws everything else off, so make sure you're doing that right. Put the S in the center and the O's on the side. Stick them together and then start making the outer guys happy. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All right, I have 16 electrons, I need 18. So I'm gonna put 2 more, and the only place I can put them is on sulfur. 18 electrons on the board. Oxygen is happy. Oxygen is happy. Sulfur is close to being happy, but not quite. It only has 6. So one of these oxygens has to give up a pair of electrons or share a pair of electrons. Now, which oxygen can do it? Oxygen 1 or oxygen 2? It doesn't matter which one you do. That makes it a resonance structure, okay? It means that that sharing is sort of oscillating between the two of them. So as far as the electron geometry is concerned, again, this is a resonance structure too. Okay, as far as the electron geometry is concerned, we are just going to look at this. We're going to look at all the electron groups. So double bonds count as 1, single bonds count as 1, a lone pair counts as 1. So there's 3 electron groups, 3 groups. So 3 groups means that we are trigonal planar. Now we need to figure out what the molecular geometry is. So what are the atoms themselves doing? It's not linear. I'm going to draw this a little bit better. So let's make it look like this. There's going to be this here. There's going to be this over here. And then there's the lone pair on top. So if I sort of ignore the lone pair and look at what's happening here, I get a bent structure, all right, or a V shape. This guy over here, pH3, I've got 8 electrons to mess around with. So P in the center, H on the sides. I'm going to stick them together. Hydrogens are all happy with 2, so we're good there. I have 2 more electrons though. The only place to put them is on the phosphorus. Boom, boom. Okay. All 8 electrons are on the board. Check and make sure everything's happy. They're all currently happy. So now we need to talk about the shapes. So as far as the electron geometry, count up my electron groups. There's 1, 2, 3, 4. 4 groups makes this tetrahedral. Molecular geometry. All right, so think about the tetrahedral shape in your mind's eye. Bring it into your mind's eye, okay? So we've got this little pyramid with this like booper sticking out of the top. Well, when we're looking at the molecular geometry, we're going to ignore the booper on the top. And we just have these 3 groups that are pushing down. So the molecular geometry for this is going to be trigonal, but it's not trigonal planar like this one where it's on a flat surface. It's trigonal pyramidal. Because the lone pairs push those 3 other groups into a subtle pyramid shape. Any questions on that? You're gonna have a bunch of practice with your Lewis dot structure lab, asking trigonal or asking electron and molecular geometry. If you can finish your lab, by tomorrow, by like 2 or 3, I can have it graded for you, or I can send it back to you with comments so that you have something like correct to study off of. So if that's something that you want to do, feel free to get that to me later on today or tomorrow, and I can help you out. There's a couple other things in this chapter we've got to talk about. So this is how to do the VESPR according to the slides. Draw the Lewis dot structure, determine how many electron groups there are, figure out how many lone pairs, and then you can pretty much reference this and it will tell you. Sometimes chemists will use different notations to represent a three-dimensional structure. So they'll use straight lines, meaning that the bond is parallel with the paper. Hashtag means the bond is projecting into the paper, and a wedge means that the bond is projecting out of the paper. So when if you've ever seen structures like this, they're trying to represent that tetrahedral shape where these two are in line with the paper. This one is coming towards you, towards the eye, and that one's moving back into the paper. So why don't oil and water mix? It has to do with something called polarity. Certain molecules are polar and other molecules are not polar. In this case, water is a polar molecule. Oil is a nonpolar molecule. Likes dissolve likes, so polar things will be dissolved by polar materials. Nonpolar things get dissolved by nonpolars. So let's look at water here. Water is our go-to polar molecule. I'm going to sort of explain this to you in the best way that I can, but an easy way to know if a molecule is polar or not is, does it have lone pairs on the central atom? Okay. So a saying is the lone polar bear. So the lone pair means it's polar, okay? Lone polar bear. So if your molecule has lone pairs on the central atom, it is polar. If it doesn't, for the most part, it won't be polar. So in order to talk about polarity, we need to talk about electronegativity. Electronegativity is a value given to atoms that tells you like how greedy they are for electrons. Okay, so if they have a high number, they like electrons. If they have a low number, they don't like electrons very much. So let's look at a chart of electronegativity. Here's a chart of electronegativity. I wouldn't expect you to memorize these. I would give them to you, but do know that fluorine has the highest electronegativity, and then they decrease as you move down towards cesium, which is the most metal-like thing. These don't have very high numbers. Why? Because they don't want electrons, right? They're always trying to get rid of electrons. Fluorine is very greedy. It wants an electron to get to the configuration of neon. Oxygen is also greedy, not quite as greedy as fluorine though. So hydrogen and oxygen don't share the electrons equally. Oxygen is greedier than hydrogen is for the electrons. So what will happen is the electrons will hang around a little bit more around the oxygen, like just more readily it's going to sit in the oxygen side. The electrons that they share will sometimes be over by the hydrogen, but in general, they're going to be pulled closer to the oxygen. So what this creates is a dipole moment or a lopsided tug of war. The hydrogen will have a somewhat of a positive end, and the oxygen is going to have a negative end. So this delta symbol with the negative is where the electrons hang out more. The delta with the positive is where the electrons hang out less. So now what we can see is that this bond is asymmetrical. We would call this a polar covalent bond. So it means that the sharing of electrons is not equal. Polar because one side is having a positive and one side is having a negative. The magnitude of this dipole moment or the asymmetry is based off of the difference between their electronegativity. So something that has a larger electronegativity difference will move more towards a polar covalent bond until it becomes ionic. I'll show you that in a second. So here are all the electronegativities. This thing here is not a polar covalent bond. We would call this a non-polar covalent bond. Why? Well, is there a difference in either of these electronegativities? No. Chlorine has an electronegativity of 3, and it's chlorine and chlorine. So both of these are going to share the electrons equally. There is no dipole moment. There is no asymmetry to the share, so we say it's nonpolar. Start to associate the word nonpolar with like balanced things and polar with unbalanced things. What happens if the electronegativity becomes very, very large? Well, at that point, the difference in electronegativity is so great. Chlorine is so greedy for the electrons, and sodium has such little interest in them that they're not even going to share them. It's just going to transfer the electrons. So sodium just says here, just take my electron, I don't care. And then we get a positive charge and we get a negative charge, which gives us the ionic. Here is a polar covalent bond. So this is where they are still sharing the electrons. So there's still overlapping of the electrons, but fluorine is greedier than hydrogen. So we have a dipole moment or a polar covalent bond. And so this is sort of the cutoff. If the difference in electronegativity is between 0.4 and 0, we just say that that's a pure or a nonpolar covalent bond. So all the diatomics are in this. If they are sharing the electrons, but not sharing them equally, that would be a difference in electronegativity between 2 and 0.4. We say it's a polar covalent bond. So they're sharing, but they're sharing imbalanced. If your electronegativity is greater, the difference in electronegativity is greater than 2. So this is when you have a metal and a non-metal, they will no longer share. It will just go, boop, here, take my electron, and then we'll stick together from our difference in charge. That whole thing is talking about bonds, okay? So the difference in, not bond, bond type. So are we pure covalent, are we polar, or are we ionic? Now I want to talk about a polar molecule. So most of the bonds that we find in non-metal combinations or molecular are going to be polar bonds, but the molecule itself won't be polar. So how can you have a molecule that's non-polar, but the bonds are polar? Well, let's look at this situation here. So carbon and oxygen do not share the electrons equally. The electrons like to hang out next to the oxygen. But the oxygen, so the bond itself, so we would say that this bond is polar, but the entire molecule, well, this dipole moment that's pulling in this direction and this dipole moment that's pulling in this direction cancel each other out. So it's sort of like a tug of war where there's a balanced pull, equal and opposite. So this structure here as a whole is nonpolar. The bond is polar, the molecule is nonpolar. So this is where that lone polar pair comes into play. There's no lone pair on this, so it's going to be nonpolar. When we have a situation like this is water. Okay, what they haven't drawn on the water are the two lone pairs. There's two lone pairs there, two lone pairs there, okay, two lone pairs there. When we have a bench structure, so there is a dipole moment. The electrons like to hang out closer to the oxygen, but we're no longer in a straight path or a linear path. We're now in a bent path, so there's this asymmetric pull in this direction of the molecule. We're going to have an overall negative charge over here and then a positive end over here. So this thing is not balanced. Sort of like, you had two ropes here and the person forgot to come to pull on the ropes. So everything's going to get pulled down. So asymmetrical. So really, as far as the molecules are concerned, you're going to be okay with this idea that if there is a lone pair of electrons on the central atom, it's polar. If there is no lone pair on the central atom, it's nonpolar. So going back to this structure over here. So if we were to look at this and I was to say, hey, SO2, is it polar or nonpolar? You would tell me that it's polar. Why? Because it has these lone pairs of electrons. Same thing with this one. Polar or nonpolar? We would say that this thing is polar because it has a lone pair of electrons on it. Some examples of nonpolar things earlier in the slides. with our simple geometry? Nonpolar, equal and opposite pole. This here, for the most part, I would say that this is nonpolar, equal and opposite pole. And then our tetrahedral shape, where everybody is paired off with the same hydrogen, we would say that that's nonpolar as well, equal and opposite. So why, so as far as why oil and water don't mix. So water molecules have lone pairs of electrons on them, so they're polar, which means that they're going to sort of stick together, or they're going to attract each other. Oil is, for the most part, nonpolar. So let's look at it like in this image here. So down on the bottom, we have all the water molecules. And because they're polar, they have a positive and a negative side, like two sides of a magnet. These things are going to stick together. So the oil doesn't have that positive negative side. So what ends up happening is the water clumps together in this sort of magnetically attracted area, and it repels the oil. Or if you were to think about having a container full of sand and like little flecks of metal, over time, the flecks of metal are going to attract to each other. If they're made out of a magnetic material, they're going to attract to each other and they're going to repel the sand out. So that's what's happening here with our oil and water. That's why when your hands are greasy and covered in oil, running water over the oil isn't going to do anything because the water can't stick to the oil. So what do you have to use in order to wash your hands or a dish if you have oil? You have to use this thing called soap. Okay, so what is happening with soap? Here's soap. This is a soap molecule. Soap is made using some sort of nonpolar material, usually a fat. If you've seen Fight Club, they use human fat in that, but usually you use some sort of like vegetable fat, soy or something like that. And you've got this long nonpolar molecule. And what you do is you take that fat molecule or that oil molecule and you saponify it, or you take it through this process of saponification, which is the process of making soap. And long story short, you take lye, you get your soap molecule, or rather your oil molecule, and you kind of cut off one end of it and you give it a polar head. So what originally was just a long, balanced, non-polar molecule now becomes a long, non-polar molecule with a polar head at the top of it. What happens is this polar head will stick to the water, and this non-polar tail can stick to the oil on your hand. So the soap has created a bridge between the water running over your hand with the polar head and the and then the grease on your hand that's non-polar. So soap is pretty cool stuff. That the last thing I think I want to talk about as far as soap is concerned. Yeah, and so we are we're done with that chapter. That's it. That's all I got for that chapter. So you're more than welcome to stay around. If there is any Lewis dot structures you want to go over from the lab, or polar, non-polar stuff, or shape stuff, stay around and we could just work on it together. Otherwise, you're free to go. And I will chat with you all on Monday. You can take your test as early as Sunday if you want to. Otherwise, I'll remind you guys on Monday. All right, so have a good afternoon. Feel free to stay around if you want to.